Welcome back to the curriculum. This is Stage 5, Lesson 38, and we're stepping into the world of multicast. Over the next few slides, we'll unpack how one-to-many delivery actually works on a network, the special address range it uses, how hosts signal interest through IGMP, and how routers build delivery paths with PIM. Think of multicast as the efficient middle ground between sending to just one device and flooding everyone. And by the end, you'll see exactly how that balance is achieved. So here's the roadmap for the lesson. We'll start by comparing unicast, broadcast, and multicast side by side so the trade-offs are clear and you know when each one belongs. From there, we'll explore the multicast address space, the 224.0.0.104 block, and the reserved ranges that live inside it. Then we'll get into IGMP, the protocol hosts use to join and leave groups, and finally, PIM, which is how routers actually build the distribution tree that carries the traffic. Let's start with that side-by-side comparison. Unicast is one-to-one, your browser talking to a web server. Simple, but every additional receiver means another full stream, so bandwidth scales linearly. Broadcast is one-to-all on the local subnet, useful for things like ARP and DHCP discovery, but routers won't forward it, so it can't leave the segment. Multicast sits between them. The source sends a single stream, and the network itself replicates it only toward the receivers who actually asked for it. That last idea, send once, replicate as needed, is the whole reason multicast exists. To see why that matters, picture a CEO town hall with 100 employees tuning in. With unicast, the source has to push out 100 separate copies. So if the stream is 5 megabits per second, the uplink suddenly needs 500. That's a saturated link that simply doesn't scale. With multicast, the source sends one stream, and a router downstream duplicates it toward each viewer. The uplink stays at 5 megabits, 100-fold saving, with the network doing the heavy lifting instead of the source. Now, for routers to deliver those streams, they need addresses to aim at, and multicast lives in its own dedicated block, 224.0.0 through 239.255, 205.25, the old Class D space. Within that block, ranges are carved out by purpose. The 204.24 slice is link local. Protocols like OSPF and RIPv2 use it, and routers never forward those packets. The globally scoped range carries things like NTP and IPTV. 2328 is reserved for source-specific multicast, where the receiver names the source directly. And 239.8 is the private playground, the multicast equivalent of RFC 1918, perfectly safe to use inside your own network. Inside that link local slice, a handful of addresses come up so often they're worth memorizing. 224.0.0.1 reaches every host on the subnet, and 224.0.12 reaches every router. Then the routing protocols each claim their own. OSPF uses 0.5 for all routers and 0.6 just for the designated and backup designated routers. RIPv2 sits on 0.9 and EIGRP on 0.10. PIM itself uses 0.13 to coordinate between routers. VRP takes 0.18 for gateway redundancy. IGMP v3 reports go to 0.22, and Toshiba is MDNS. That's what Bonjour and Avahi use for service discovery on your local network. So how does a host accurately tell the network it wants one of those streams? That's the job of IGMP, the Internet Group Management Protocol. It runs between hosts and their local multicast router, the one we call the IGMP query. And it really only has 3 conversations. The query periodically asks who wants what. Hosts reply with a report to join a group, and from version 2 onward, they can send a leave to opt out cleanly. Version 3 is what you'll see most often today because it lets a host filter by source, not just give me group X, but give me group X from this specific sender. Now, IGMP only handles the last hop, the conversation between hosts and their local router. But what about getting the stream across the wider network to that router in the first place? That's PIM's job. Protocol Independent Multicast builds the actual distribution tree between routers, and it comes in 3 flavors. Dense mode floods everywhere and prunes back. assumes most subnets want the stream, which is rarely true anymore, so it's mostly legacy. Sparse mode flips that assumption. Few subnets want any given stream, so routers explicitly join a tree through a rendezvous point, the RP, and that's your enterprise default. Source-specific multicast skips the RP entirely because the receiver already knows the source IP. It just asks for that exact source group pair, which is how IPTV and market data feeds work on 232.0.0.08. Let's put it all together and watch a stream travel end to end. The source just blasts packets to 239.1.1.100. It has no idea who's listening, and it doesn't need to. When you click play, your app tells the OS to join that group, the OS programs the NIC, and your host fires off an IGMP report saying, "I want this group." The local router hears that, and now PIM kicks in. It sends a join toward the rendezvous point, and each router along the path adds an outgoing interface, building a branch back toward you. Packets start flowing, and when you change the channel, an IGMP leave goes out. The router checks if anyone else still cares, and if not, PIM prunes the branch away. That's the whole life cycle. So where does all this actually show up in the real world? IPTV is the classic case. Your ISP streams hundreds of channels using the 2.2.0.8 SSM range, one source per channel, thousands of homes tuning in. Financial exchanges live on multicast too, pushing trade data to traders in microseconds where unicast simply couldn't keep up. Corporate town halls over WebEx, macOS patching with sccm, and even your routing protocols, OSPF on 224.0.5 and 6, EIGRP on 224.0.10, they're all multicast under the hood. Once you start looking, it's everywhere. But for all its elegance, multicast is famous for breaking in frustrating ways. The Big Five, forgetting to enable PIM on every single hop in the path. Miss one interface and your tree dies there, leaving IGMP snooping off, so your switch floods multicast like it's broadcast, an unreachable RP that takes down every group with it, firewalls silently dropping 224 anything at the boundary, and old hosts that can't speak IGMP Vita 3, so SSM joins just never happen. Each fix is small, but you have to know where to look. So let's pull the whole lesson together. Remember the core idea. Unicast goes one-to-one. Broadcast hits everyone, and multicast threads the needle by delivering only to those who asked. The address space lives under 224.0.0.04 with link local, source specific, and admin scoped ranges carved out. IGMP is how hosts subscribe. PIM is how routers accurately build the tree behind the scenes, usually PIM sparse mode with a rendezvous point. And you'll find it powering IPTV, trading floors, conferencing, and even the routing protocols running your network. And here's your cheat sheet, the things worth keeping close. Multicast lives in the Class D range, with 224.0.0024 staying link local, 2328 reserved for source-specific delivery, and 239.8 acting like the private space of multicast. Memorize a few well-known addresses too. 0.5 and 0.6 for OSPF, 0.13 for PAIM, 0.18 for VRP. And remember, IGMP is how hosts join, with version 3 being today's default because it can filter by source. And that wraps up our deep dive into multicast. Up next in Lesson 39, we shift gears to something every network quietly depends on: network time and the protocol that keeps it all in sync, NTP. You'll see why every device, from your switches to your security logs, has to agree on what now actually means. I'll see you in the next one.